Awesome. Excellent. Well, howdy, everybody. I'm Joshua Nicely. I'm going to be giving you an introduction to ASF and some of the really basic information about SAR. Uh, so to start off about ASF, we are a DAAC, that is a Distributed Active Archive Center. There are about 12 of them distributed through the US. And really what we do is we collect, uh, process, analyze, and distribute data for other people, for scientists and engineers to use. Uh, if you have ever used radar data before, you may notice it can be a bit difficult, to put it mildly, to write the code to use radar data. So a really big part of what ASF is trying to do is put together these recipe notebooks where all the code is already written out, and users like yourselves just have to take that code and change a few simple inputs rather than having to spend days, weeks, or even months writing your own code. All right, it's about some of the benefits and unique characteristics of SAR. SAR is pretty amazing, especially for 27 monitoring. It is an active source, which means that it gives out its own signal and receives its pulse back. So we don't have to wait for, like, for example, with optical imagery, we don't have to wait for the sun to be up. We can get imagery of the surface day and night. The other thing that's really amazing about SAR is the particular wavelengths that we use for it. Uh, Radio signals, for what we're talking about, are usually in about the 1 centimeter to 1 meter range. And when we're looking at the Earth's atmosphere, those wavelengths, for the most part, pass through everything. They're going to go through clouds, they're going to go through rain, through smoke, uh, most volcanic ash. So basically, no matter what kind of hazard is happening on the ground with SAR, we can still see past it and look to the surface and see what's going on. Uh, I just want to point out, SAR is not a replacement for optical sensors. Uh, Optical and SAR and even other things like near infrared, they can be complementary. They all give different information. Some of it is overlapping, but they do not replace each other. Right. One of the really great things, and an example here, is time series that we can do with SAR. Uh, with SAR satellites, their orbits tend to be extremely well known and extremely stable. And to get images of the ground from the same viewing geometry in the same exact space. And so we can create these great long time series like this. So now, about forming a radar image, there are kind of one really important thing to get from this slide is then that is that we are dealing with a side-looking geometry. With the way that radar works, if we're looking straight down, we're not going to get the data that we need in a way that we need so that we can produce an image. We're just going to get an altimeter pulse, just a measure of distance to the ground. In order to get an actual image, we have to look off to the side. And that's really important. It ends up, that combined with the fact that we're using an active sensor, ends up creating some geometric distortions that we'll talk about later and that are really important to deal with. One other thing, azimuth, that's going to be in the direction of the satellite that it's moving, and range is looking off to the side. All right. So there are limitations of SAR, uh, uh, exemplified by this example on the top right. Basically, our resolution decays with distance. That's the same thing happens with optical. Uh, if we're looking at the ground, if we have a 10-meter sensor in the sky looking at the ground from about 850 kilometers, which isn't too big of a distance for SAR satellites, uh, our ground projected resolution is going to be about 5 kilometers, which isn't terrible. That's what we have for Venus, and I've used that a lot. But when we're talking about Earth, we usually want something a lot better, something more like 10 meters. And if we're going to get that 10-meter resolution, we need about a 5 kilometer long antenna, which is absolutely ridiculous and just impossible and something that we can never produce. But there are tricks to getting something like that. And that's when we do this by creating a synthetic aperture. There are two different ways to think about this. There's uh, this way and then the Doppler explanation that I don't really get. So I'm going to talk about this kind of geometric explanation. Uh, Whenever we have that satellite in the air, or in orbit, it's still going to be looking at the ground and seeing this gigantic swath every single time it gets an image. And as it moves over, it gets overlapping swaths again and again and again. And the thing is, if we get enough of these overlapping swaths, we can combine them to sharpen the image to something much, much higher resolution. And basically, we fake having this gigantic, super long aperture by combining all of these images. Uh, there is some important assumptions in this. With this, in order to do this, we assume that everything on the ground is static, that nothing is moving around. If you ever see images with vehicles in them, like cars or boats while they're moving, because they're moving and they don't have a non-zero velocity relative to our reference frame, uh, they're going to be shifted in position away from where they would be. And it might look like that car, instead of being on the road, is somehow driving on top of a forest right next to it. But for the most part, we can assume everything is static. All right. All right, components of the SAR data set. There are really two big pieces. The first is amplitude, and this is basically just the backscattered signal that comes to us. Uh, this gets impacted by a whole bunch of things. We have the sensor properties, we have the target characteristics, we have viewing angles, which we'll get into more. Uh, and the amplitude, that's what gets used to create these grayscale images of radar that we see so very often. Phase is a little more complicated. This has to do with the location of the signal along its wave cycle when it returns to the sensor. So whenever we send out a radar pulse, it is an oscillating electromagnetic wave. And we can use the fact that it's an oscillating wave to help us get some really, really high resolution distance measurements. And it's the basis for SAR interferometry. All right, so about NSAR. To do NSAR, we need kind of two general things. Uh, well, two things. We need a repeat pass geometry in which our satellite is looking at the ground at almost exactly the same position from exactly the same incidents. There's some wiggle room, and there is stuff you can do with actually having some different baseline that'll give you something slightly different from INSAR, but very similar. But if we just want a distance measurement, we want to have them passing directly over each other. And what we do is we take those two phase maps. Yeah, I'm getting ahead of myself. Uh, and so when the satellite passes over, sends down a radar signal, uh, oscillates back and forth, hits the ground at some point in its oscillation, and then goes back. Well, if there's been ground movement, the point at which it hits the ground at a particular point in its oscillation is going to be different. And we can use that difference in that phase to figure out distance. And basically just take the two phase maps that we get from the repeat passes and subtract them from each other. And they'll get these beautiful interferograms, which are amazing and they're really cool. But looking at them, you can see that there is no elevation height inherent in this. We have to do some processing with this called phase unwrapping, in which we basically pick points. Well, a computer program does this. We pick points that are way off away from where we think change has happened. And then the computer program walks in, figuring out how many fringes have been passed and turns that into elevation, to a change in elevation, and then maps all that together into one single cohesive map of elevation change. It's a really powerful thing. The elevation difference to which it's sensitive depends on wavelength. This can get down to, if you're using really short wavelengths like C-band, about half a centimeter elevation difference. If you're using longer wavelengths like L-band, which is about 25 centimeters, you're looking more at like a few centimeters at best in terms of the elevation difference you can get. All right, so some of the basic operating principles for backscatter. So radar images, they're formed by the backscatter from the surface. We send out some signal, it hits the ground interacts with it and sends signal back out. And there are really three basic types of interaction to go over and a fourth special one that I want to talk about. On the left, we have specular reflection. Now this happens when the wavelength that we're dealing with is, well, this happens when the topographic variation of the surface that we're looking at is much smaller than the wavelength, something around the wavelength divided by 25 or smaller. when that happens, we get this specular reflection where it bounces off just like a mirror. When we have calm water, it happens there really, really well, like really, really well. It's very clear. Uh, when the surface starts to get rough, starts to have topographic variation, basically greater than about the wavelength divided by 4, that's when we start getting into diffuse scattering. This is when the scatter just gets spread everywhere and more Lambertian surface. Uh, Next, we have volume scattering. This one gets a little more complex. It involves polarization of the signal. Basically, with volume scattering, there are a whole bunch of really small scatterers, small compared to the wavelength of the radar wave that's being sent down. And these scatterers have a bunch of different orientations, and they end up bouncing the wave around in a whole bunch of different directions. And the really important thing about this is that it depolarizes the wave, which it's going to come up later more. And then the special case that we have is dihedral reflection. This is basically where we have right corners acting to send the radar wave directly back to the sensor with most of its power, a really large signal. This generally happens with urban areas if they have the right orientation compared to the sensor, or with tree trunks, and sometimes with agricultural growth, though it's a bit more rare with that. All right, backscatter characteristics. So the backscatter that we get is determined by both sensor and target characteristics. With the sensor, the wavelength matters. That changes how much depth of penetration we get and whether or not something is considered smooth or rough. The polarization matters, whether we have a vertically polarized wave or a horizontally polarized wave. Incidence angle is pretty important. Whenever we look at the ground with our side-looking geometry, the radar wave is not looking at just the ground at a single angle. As we sweep out, the angle of incidence with the ground changes, and that changes the way in which the radar wave interacts with the ground. It's usually pretty easy to deal with, but something good to keep in mind. Another big thing is look direction of the sensor. This is really important. Whenever we have a sensor orbiting the planet, it's generally looking in one direction, just off to, like, say, the right. During its ascending phase, that means it would be looking east. With most of these satellites for SAR, they are polar orbiting. So as they go over the top of the Earth and start their descending phase, now they're looking west. Now, this can be both good and bad. It's good because the different angle of view can give us some different information. The bad part is that there isn't really a good way yet to combine these opposite look imagery. With the way that SAR works, just the backscatter characteristics that we get are so different that getting a computer to automatically look at them and make sense of them is something we haven't figured out yet. It's an active area of research. So whenever we're dealing with these sensors and going through a workflow, it needs to be either all ascending or all descending. Now we can combine the workflows, the products afterwards together to get more information, but we can't do them at the same time. All right, and then target characteristics, this really changes the backscatter that we're going to get. One that doesn't get mentioned explicitly here is surface slope of the ground. That's an important one. Surface roughness is a really big thing that determines how much backscatter occurs, whether we're going to get specular reflection or we're going to get a Lambertian diffuse reflection. And then another really big important thing is changes in dielectric properties. This is usually associated with moisture in the ground. The more moisture, the higher the change in dielectric properties, which means the less depth of penetration that we're going to get, and the stronger backscatter that we're going to get. Just as a quick example, like if we were looking at ground in the jungle, where it tends to be really, really wet, we're only going to get maybe a few millimeters of penetration with that radar signal, and everything's going to be bouncing off of the surface, basically. But if we're looking at, say, the Sahara Desert, where there's basically no water, we can get as much as 50 meters of penetration through that sand. All right, so a little bit about the microwave spectrum. So we operate with radar from about 1 centimeter up to about 1 meter in wavelength. Uh, Now, these shorter wavelengths, we generally don't actually use them for radar imagery because they get affected by other things. There's some SO2, or not SO2, H2O absorption. And so generally, the shortest wavelength that we use for looking at the surface of the Earth is X-band, which is around 3 centimeter wavelength. Uh, that's the shortest one. The two most common that get used, though, are C-band, which is about 6 centimeters. This is what the Sentinel-1 systems are, and they're amazing. And then we have L-band, which is about 20 centimeters in wavelength. The NISAR system is going to have an S-band on there, which is pretty cool. That's going to give us another wavelength to look at. And when we have more wavelengths, we can get more information. And lastly, I'll mention that we have the P-band. This one isn't very common. It's the longest wavelength that gets used in radar. It's usually used for biomass estimation. The reason it doesn't get used all that much is because it gets interference from uh, other things that we use, like cell phones and TV transmissions and stuff like that. All right, so the influence of wavelength on signal penetration is pretty straightforward. The longer the wavelength, the greater the depth of penetration. And so that really determines what kind of wavelength you're going to want for what purpose. So as an example, if we look at an X band when we're dealing with vegetation, it's going to, because it's a short wavelength, only about 3 centimeters, we're basically just seeing what's at the top of a canopy. Whereas if we go from X to C to L band with its about 20 centimeter wavelength is going to basically just go through all of the trees, hit the ground, interact with the ground, and come back. It will be affected by some of that volume scattering, just not nearly as much as C or X band. And the same thing happens when we're talking about dry alluvium or even glaciers. Longer the wavelength, greater the depth of penetration. All right, and this is just an example showing that on the left, we have X band, and on the right, we have P band. And we can see that on the left, the X band is basically interacting with the top of the forest canopy and gets scattered from there really, really well, very effectively. But if we look at the P band, we see that there is a huge amount of penetration. We're seeing basically none of the canopy, and it's going down to the surface, and we can see it interacting and bouncing off tree trunks and some human-made structures. All right, next important thing, we have polarization. This one is a little more complicated, but it's really useful and really important for us to keep in mind. So polarization refers to the orientation of the electric field. We can do a whole bunch of different orientations. Generally, sensors, we have four different things. We either do horizontal compared to the Earth, vertical compared to the Earth. Sorry, not four things, two different things. When we're looking at these, we have basically two letters to describe whether we're transmitting and receiving in. First letter tells us what we're transmitting in, second, what we're receiving in. So HH would be transmit horizontal, receive horizontal. VV would be transmit vertical, receive vertical. We can also do cross-polarized, in which we transmit horizontal and receive vertical, or transmit vertical and receive horizontal. Theoretically, and in just about all actual applications, HV and VH are identical. So if you're getting one of them, you're getting the other. With things like the satellite or with the Sentinel system, they generally transmit, they actually do something called dual pol, where they will transmit in one orientation and receive in two others. And that gives us a lot more information. You can also do circularly polarized waves and elliptically polarized waves. That gets a lot more complicated, but it can be very useful for finding out other information about the surface. And all of these different polarizations affect how the radar waves interact with the surface and what information we're getting back. All right, awesome. And so about radar interaction with objects on the surface, this is about how those different polarizations affect what information we're getting. All of this is to first order, so it's not just like this, but it's pretty close. When we're talking about uh, rough surface scattering, it's basically like rocks on the ground or topographic undulations. If you want to look at that, we want to use VV polarizations for the most part. If we're mostly interested in things like double bounce scattering, like that dihedral reflector, or finding tree trunks, or looking at urban areas, uh, we want HH. And then when it comes to volume scattering, this is something that's a bit more complicated. Like I said before, it has to do with having lots of small scatters compared to the wavelength that's being used, and causing a whole bunch of uh, scattering and reflection events that depolarize it. And whenever we're looking at something that happens like this can happen in a tree trunk, or not, sorry, not tree trunks, tree canopies, and in sand or dry alluvium. Uh, oh yeah. When we're looking at this, basically it takes the energy from the transmit that we gave and then redistributes it into all the other possible polarizations. And so when we're looking at volume scattering, what we generally expect is for all of the signal strength to be decreased that we're getting back. All right. And so this image just gives an example of those kind of three end members, looking at uh, specular, volume, and corner reflecting. So if you look at the far right, we have this specular reflection from a lake. It's a calm day. There's very little going on with the water. And so it just bounces off and goes straight downrange away from the sensor, and we don't see anything. If there was wind, we would see that roughness on the surface. And it's actually something that gets used to figure out wind speeds on the ocean. Uh, Looking at the far left, we have a corner reflector with a building. Sorry, not a corner reflector, dihedral reflector. Corner reflectors are very special equipment that are used to calibrate radar sensors. Uh, and so this building is basically directly perpendicular with our radar sensor, and it's giving us a really strong return because of that. Uh, if the building wasn't directly perpendicular, which sometimes happens in different neighborhoods, we get a much weaker reflection. And then down in the center here, we have uh, volume and roughness scattering. The particular wavelength that we're using here is a little bit shorter, so we're getting both some roughness scattering from the surface, that VV, but it's also combined with some of that volume scattering that happens. All right, last slide. This is a pretty important one, radiometric terrain correction. So if we look at this image on the left, this is where we see those terrain distortions that happen with the fact that we're using an active sensor. Everything in here looks like it's leaning to the left, which is toward the sensor, and everything on the left side looks brighter. And that has to do with those with that the topography. Basically, since we're sending out a signal, uh, it goes down to the ground in this gigantic wave. And if there's something with positive topography, that lifts it up and moves it closer to the sensor, which means our return from it is going to be sooner. And so what this does is that it takes the sensor side of things like mountains and compresses them and brightens them. Whereas the opposite side, uh, the sensor, basically effective surface area is reduced. So it's extended and darkened. And we can see that with all these mountains in here. That's what we have to do, is a radiometric terrain correction to deal with this, to get rid of those terrain distortions, and then also correct the brightness values. And in order to do this, we have to have a digital elevation model. The quality of our RTC is very much dependent on that DEM. For Earth, we're lucky in that we have some really high quality DEMs. Uh, the old school one that a lot of people still use is the SRTM mission, the Shuttle Radar Topography mission. But there are also much higher resolution things. And we can actually create DEMs using NISAR. So we don't have to just have some pre-existing system. And then once we do our RTC, we end up with something like this on the right, where the mountains have been shifted back into their correct position. and the brightness values are they correspond more to the material itself and the scattering properties itself, rather than just to the surface area that is shown to the sensor. There are some spots, like up here, where it is very dark still, and this has to do with shadow. With some areas, if it is too tall, the radar wave just simply won't get to the other side. And so we don't get any information and it's just dark. And, right. And with that, I'll be handing it over to Dr. Eric Fielding.